Imagine pointing your spacecraft at a planet you can see, a world so close it's practically a neighbor, and watching it slip away from you, again and again, for 30 straight years. No technology you have can make it stop. It's not that you can't get there, it's that you can't stay. This actually happened, and it's only the beginning, because nearly every world in our solar system has a defense like this, a single weapon that turns "just go there" into one of the hardest problems humans have ever faced. Today, one planet at a time, we're going to find out exactly what each world uses to keep us out, and why the answers get stranger the farther we go. Start with a fact that tends to break people's intuition. If you average it out over years and decades, the planet that spends the most time nearest to Earth is not Mars, the world everyone dreams about. It is Mercury. The tiny scorched marble closest to the Sun is, on average, our nearest planetary neighbor, because while Venus and Mars swing wildly toward and away from us, Mercury hugs the inner system and never wanders far. So here is a world practically next door, and yet it took 30 years between our first visit and our second. 3 decades of silence for a planet we could see with the naked eye. Why? The first answer is heat, but heat is not the real villain. Mercury's daytime surface climbs to around 430 degrees Celsius, hot enough to soften lead, and any machine that goes there has to hide behind a shield kept permanently aimed at the sun, like someone shading their eyes on a beach that never has shade. Engineers have solved harsher thermal problems than that. The shield is the easy part. The real defense is speed. The sun is the heavy weight of the entire system, and its gravity does not gently tug at things that fall toward it. It hurls them. Aim a spacecraft inward and it does not drift down toward Mercury. It plunges, accelerating the whole way, arriving with so much velocity that the little planet's weak gravity has no hope of catching it. The craft would simply scream past and keep going, swallowed by the sun's pull. To actually stop at Mercury, you have to shed an enormous amount of that speed, and small robotic probes do not carry the mountains of fuel that braking would demand. For 30 years, that was the wall nobody could climb. The solution, when it came, was almost poetic in its patience. Instead of charging at Mercury, you sneak up on it. The Messenger spacecraft, launched in 2004, did not fly to Mercury so much as orbit the Sun again and again, looping past Earth, then Venus twice, then Mercury itself 3 times, letting each close pass nudge its speed and bend its path. Every flyby trimmed its velocity relative to Mercury until the planet could finally grab hold. The journey took nearly 7 years and covered billions of kilometers to reach a world we could have pointed at from our backyard. Messenger finally settled into orbit in 2011, mapped the whole surface, and found hints of ice hiding in craters near the poles that sunlight never reaches. Frozen water on the hottest planet's doorstep. When its fuel ran dry in 2015, controllers let it fall, ending the mission with a crater of its own. The lesson Mercury teaches is uncomfortable. Nearness means nothing. The sun decides who visits, and the sun does not make it easy. Step 1 world farther from the sun, and you reach the planet that should have been our sister. Venus is almost exactly Earth's size, made of the same rock, born in the same neighborhood, from the same cloud of dust. At its closest approach, it swings nearer to us than any other planet ever does. A near identical world, right beside us, the most reachable target in the whole sky. And it is, without exaggeration, one of the most efficient killers in the solar system. We have sent more than a dozen landers down to its surface. Most of them died in minutes. The ones that lasted longest survived only about 2 hours before the planet crushed them into silence. What makes Venus so lethal is not distance. Getting there is easy. It is the air. Venus is wrapped in an atmosphere so thick and heavy that standing on its surface would feel like sitting beneath nearly a kilometer of ocean. The pressure would flatten an unprotected spacecraft like a soda can underfoot. That atmosphere is almost entirely carbon dioxide, and it traps heat with such ruthless efficiency that the surface sits at around 465 degrees Celsius, hotter than Mercury, even though Venus is nearly twice as far from the Sun. Let that sink in. The closer planet runs cooler than the one behind it because Venus has smothered itself in a runaway greenhouse so extreme that lead would melt into puddles on its plains. And above all of that float clouds, not of water, but of sulfuric acid, raining down a corrosive drizzle that never reaches the ground because the heat boils it away first. So a lander arriving at Venus has to fall through acid, then survive pressure that would implode a submarine, then keep working in an oven hot enough to soften metal, all at the same time. Engineers have built machines tough enough to send back a handful of photographs from that surface. Eerie, orange-lit images of cracked rock under a sky the color of rust, but only ever for a few fragile minutes before the planet won. This is the great irony of Venus. It is the easiest world to reach and very nearly the hardest to stand on. Earth's twin became its opposite, and it guards its surface with a weapon no other planet uses: the simple smothering weight of its own poisoned air. Now turn around and face outward to the planet that lives rent-free in the human imagination, Mars. We have been promised footprints there for half a century. We have rovers crawling across its rust-colored plains right now, drilling, sniffing the air, photographing sunsets that glow blue instead of red. Robots have made it look easy. So why has no human boot ever pressed into Martian soil? Strip away every other complication, and one answer sits underneath all of them: distance. And the time distance forces on you. We send people to the International Space Station constantly, and it feels like deep space, but that station orbits only a few hundred kilometers up, barely a hop above the atmosphere. Even the moon, which felt like the edge of everything in the 1960s, sits about 1,000 times farther than that low orbit, and we crossed it in 3 days. Mars is a different category of journey entirely. At its closest, the gap between the two worlds is tens of millions of kilometers, and that brief window of nearness opens only about once every 2 years before slamming shut again. A crewed mission would mean months falling outward through empty space, a long stay waiting for the planets to realign, and months falling home, well over 2 years away from Earth, with no resupply ship, no rescue, no turning back. That stretch of time is what poisons everything. More time means more food, more water, more air, more spare parts, more shielding against the radiation that bleeds through interplanetary space. And every kilogram of more demands more fuel to push it, and more fuel to slow it down at the far end, and still more fuel to ever come home. The mass multiplies against itself. A single Mars trip would swallow hundreds of tons of propellant, far beyond what any one rocket can lift, which means assembling the pieces in orbit across many launches before anyone even leaves. And then there is the body itself. Months of weightlessness weaken bone and muscle, and astronauts would have to arrive on another planet already drained, with no medical team waiting. Add the loneliness, Earth shrinking to a pale dot, every conversation delayed by minutes, because not even light can outrun that distance, and you begin to understand why the experts keep saying the same careful thing. It is not that Mars is impossible. It is that Mars demands a scale of planning, money, and patience we have never assembled all at once. The red planet does not slam a door in our faces. It simply makes the hallway impossibly long. Keep going outward, past the asteroid belt, and you arrive at the king. Jupiter is so massive that all the other planets could be poured into it with room to spare. And at first, that mass seems to help us. Its gravity reaches out and pulls spacecraft in for free. So getting to Jupiter is, oddly, not the hard part. The hard part is stopping. A probe that races out to Jupiter arrives moving at tremendous speed, and a spacecraft going that fast does not enter orbit. It whips around the planet and keeps right on flying, the way the early Voyager probes did, using Jupiter only as a slingshot to fling themselves deeper into the system. To actually stay, a craft has to fire its engine hard at exactly the right moment, bleeding off just enough velocity to be captured without falling helplessly into the clouds. Too fast and you escape forever. Too slow and the planet eats you. And it would eat you. Jupiter has no ground. There is no surface to land on, no place to set down, just an atmosphere that grows thicker and heavier and hotter the deeper you go, until the pressure crushes anything that descends into a smear of vapor. We know this because we tried it. One probe was deliberately dropped into that atmosphere and survived less than an hour, transmitting data as it was squeezed and roasted before going silent forever, exactly as planned. But the cruelest weapon Jupiter wields is invisible. The planet is wrapped in radiation belts so violent they can fry electronics from the inside out, scrambling circuits and killing instruments before a mission is supposed to end. Spacecraft sent there must be armored and must thread careful orbits that dip in and dart out, never lingering in the worst of the storm. Even so, the giant takes its toll. When these missions end, controllers usually steer the dying probes straight into Jupiter on purpose, not out of cruelty, but to make sure the wreckage never drifts down onto one of the icy moons, where a hidden ocean might be waiting, and where a stray piece of Earth could contaminate something we have not yet had the chance to understand. Jupiter, it turns out, is easy to reach and brutal to befriend. Saturn is the postcard of the solar system, the world everyone draws when they draw space, and reaching it announces a threshold. Beyond this point, the sun stops being a power source and becomes just another bright star. Out here, sunlight is too thin and weak to feed solar panels, so any spacecraft bound for Saturn or farther has to carry its own power, a generator that turns the heat of slowly decaying radioactive material into electricity. These power packs work for decades and ask for nothing, which is exactly why we use them, but they are heavy, and weight is the enemy of every mission. Heavier craft need bigger rockets and more fuel and far bigger budgets, and the cold of the outer system means insulation has to be wrapped around everything just to keep the instruments from freezing solid. Then there is the raw distance, well over 1 billion kilometers, which is why every probe that has reached Saturn first stole a speed boost from Jupiter along the way, using the giant's gravity as a launching ramp toward the rings. Only a handful of spacecraft have ever made the trip, and only one truly stayed, the Cassini orbiter, which spent 13 years circling Saturn and revealing it in detail no telescope could ever match. But Cassini carried a passenger, and that passenger pulled off something staggering. A small lander detached and parachuted down through the orange haze of Titan, Saturn's largest moon, and touched down on a surface no human had ever seen. What it found looked eerily like home: riverbeds, shorelines, hills carved by flowing liquid, except the rivers there run with frigid methane instead of water, and the rain that fills them is methane too, in a deep frozen world, hundreds of degrees below anything we know. Cassini also caught towering plumes of ice spraying off the tiny moon Enceladus, the fingerprint of a hidden ocean buried beneath its frozen shell. When the mission ran low on fuel, the team chose its ending deliberately, rather than risk the craft someday crashing into one of those possibly living moons. They sent Cassini diving into Saturn itself, gathering data the whole way down until the planet swallowed it. Saturn sits right at the edge of what we can comfortably reach. Step 1, rung farther out, and difficult becomes something else entirely. Here is a planet that has been visited exactly once, for a few hours, by a probe that was only passing through on its way to somewhere else. Uranus. We have studied it for decades through telescopes and sent it precisely one fleeting glance up close, back in the 1980s, and then we turned away and never came back. It is one of the most neglected worlds in the entire system, and that neglect is not because it is dull, it is because it is far, and far is expensive, and Uranus is anything but dull. It is the planet that fell over. Every other world spins more or less upright as it circles the sun, but Uranus rolls along its orbit tipped almost completely onto its side, as if something enormous knocked it sideways long ago. This produces seasons unlike anywhere else. Each pole gets roughly 4 decades of unbroken daylight, followed by 4 decades of unbroken night. Imagine a winter that lasts 40 years. The sun simply gone from the sky for longer than most human careers. Beneath its pale blue-green haze, Uranus is an ice giant, a slushy mix of water, ammonia and methane wrapped around a rocky heart, with the coldest atmosphere of any planet, a place where the temperature plunges below -220 degrees Celsius. So why do we keep skipping it? The planet sits roughly 20 times farther from the sun than we do, which means any mission would spend somewhere around 15 years simply getting there, surviving on nuclear power because sunlight is useless at that range. A signal from a craft there would take hours to crawl back to Earth, so the spacecraft would have to make most of its decisions alone, with no one to call for help in the moment. And there is a quieter problem nobody talks about. keeping a team of engineers and scientists together for the decade or two it takes to plan, launch, and finally arrive. People retire, people move on. Knowledge slips away between hands. Missions have died not from engineering failure, but from the simple human difficulty of staying committed to a goal that won't pay off until the people who started it are nearly gone. Uranus does not defend itself with heat or radiation. It defends itself with patience, by being so far and so slow that we keep deciding to wait just a little longer. And then there is the last true planet, the one at the very rim of the Sun's family, Neptune. Like Uranus, it has been visited only once, by a single spacecraft that flew past in 1989 and changed everything we thought we knew in just a few hours. In that brief encounter, we learned more about Neptune than in the century and a half since its discovery. That it has rings too faint to see from Earth, hidden moons, and storms of impossible violence. That violence is its own mystery. Neptune is so far from the Sun that sunlight there is feeble, almost nothing. And yet it has the most ferocious winds in the entire solar system. Gales screaming faster than the speed of sound across the cloud tops. On Earth, the sun drives our weather. Out at Neptune, the sun barely reaches, so something inside the planet, some slow leak of leftover heat from its birth, must be powering those winds, and we still do not fully understand it. A deep blue world wrapped in supersonic storms, lit by a sun no brighter than a distant lamp. Reaching it means everything that makes Uranus hard, only more so. It is over 4 billion kilometers away. The journey stretches across 15 years or more, even with a gravitational boost from Jupiter, and the windows to use that boost open only about once a decade. Yet there is a reason scientists keep arguing that Neptune, not closer Uranus, should be our next great destination, and that reason has a name: Triton. Neptune's largest moon orbits backward, the wrong way around its planet, which almost certainly means it did not form there at all. It was a wanderer from the frozen outer belt, captured long ago by Neptune's gravity. Triton is one of the few worlds beyond Earth known to be geologically alive, with geysers of nitrogen erupting through a crust of ice. And beneath that ice there may well be an ocean of liquid water. A captured world, hiding a sea, circling the most distant planet in the wrong direction. That is the prize sitting at the farthest door, and we have only ever knocked on it once. Push past even Neptune and you reach a place that has been argued over more than almost any object in the sky. Pluto, once crowned the 9th planet, later stripped of the title and recast as a dwarf among countless icy cousins, Pluto sits more than 6 billion kilometers away, and for most of human history, it seemed hopelessly out of reach, a smudge of light that might take centuries to visit. Mission after mission to Pluto was dreamed up, and then killed, almost always for the same brutal reason. It was too far, and too far meant too expensive. Plans were drawn for grand tours and tiny featherweight probes and everything in between, and one by one budgets erased them. Each cancellation hurt more than the last, because Pluto's orbit was carrying it slowly away from the Sun, and scientists feared its thin atmosphere would freeze and collapse onto the surface if we waited too long. There was a clock ticking, and we kept failing to beat it. When a mission finally launched, it could not afford to stop. The New Horizons probe was flung outward in 2006, stealing speed from Jupiter on the way, and after nearly a decade of falling through the dark, it reached Pluto in 2015. And then it did not slow down at all. There was no fuel for braking, no orbit to settle into. It simply raced past at tremendous speed, cameras working frantically, capturing in a single afternoon the sharpest images ever taken of a world that had been a blur for 80 years. And what it found stunned everyone. Not a dead grey rock, but a place with mountains of water ice, vast smooth plains, and signs of recent geological activity, including a giant heart-shaped basin that became instantly famous. A world we had nearly given up on turned out to be alive with detail. New Horizons then kept going, deeper into the dark, because there was never any way to make it stay. Pluto's defense was the simplest and most final of all. It lived so far away that we only ever got to glance at it once, in passing, before it vanished behind us forever. And now we step off the edge of the map entirely, because as hard as every world we have discussed has been to reach, they all share one mercy. They belong to our sun. They are, in cosmic terms, in the same room as us. The moment you ask about reaching another star, the difficulty does not grow. It explodes into something the human mind can barely hold. Consider the fastest thing we have ever launched, a probe that has been flying outward for nearly half a century and is now drifting beyond the solar system at around 17 kilometers every second. It is breathtakingly fast by any earthly measure. And at that speed, to reach the nearest star to our sun, it would take roughly 76,000 years. Not 76. 76,000. Whole civilizations would rise and crumble while it crossed the gap. The distance is so vast that our best chemical rockets are not merely inadequate, they are absurd. To reach even a small fraction of light speed using ordinary fuel, you would need a ship more massive than entire planets, a thing that could never be built. So the dreamers have looked elsewhere. Ion engines and nuclear thrusters could one day cross our system efficiently, but they would still take tens of thousands of years to reach the nearest star. Plasma rockets, fusion bomb propulsion, enormous sails unfurled to catch sunlight, or the push of giant lasers. Each idea shaves the journey down from tens of thousands of years to thousands to hundreds, and in the boldest visions to mere decades. One of the most serious proposals imagines a swarm of featherweight chips, each no heavier than a paperclip, driven up to a fifth of the speed of light by a battery of ground-based lasers, racing to the nearest star in a couple of decades, and beaming home a handful of photographs of a world that might just resemble our own. It is, for now, mostly a sketch on paper, but it is the first sketch in history that does not collapse the moment you check the math. So we have walked the whole way out, from the scorched neighbor we can barely catch to the star whose distance defeats imagination. And at every step the same truth kept repeating in a new disguise. Mercury hides behind speed. Mars hides behind time. Jupiter hides behind radiation. The ringed and tilted and distant giants hide behind cold and darkness, and the simple, grinding patience that distance demands. Pluto let us look only once, and the stars do not even pretend to be reachable yet. It would be easy to hear all of this as discouragement, proof that the cosmos is closed to us, that we were meant to stay home. But notice what actually happened at every one of those locked doors. We did not stop. We invented a way to sneak up on Mercury by orbiting the Sun 15 times. We learned to slingshot off one giant to reach the next. We built generators that turn radioactive decay into decades of power for places the Sun forgot. We sent a probe screaming past Pluto and caught a heart written across a frozen world. Every defense the solar system raised, we eventually answered, not with brute force, but with patience and cleverness, and with the willingness to begin missions whose payoff we might not live to see. That is the quiet thing worth carrying with you when you next look up. The planets are not lanterns left on for an easy guest. They are sealed rooms, each locked in its own way, and the whole story of space exploration is the story of a species slowly, stubbornly learning to pick those locks. We have opened most of them now, at least a crack. The stars remain shut, but every door we ever opened was once the door everyone swore could never be opened at all. So here is the question to sit with as the screen goes dark. Of all the locked doors still ahead of us, which one will we learn to open next? And will it be us who walks through, or only the children of the people watching this today?